Hello, and this is the Exam 3 review with that for spring 2017. So with that, this is going to be the free answer portion of this. There's also obviously going to be some multiple choice questions on general concepts. So with that, but for here you're going to see the free answer. So these here we're going to add either HCl or HBr to a conjugated alkene here, stuff like that, and so these always end up working the same way. It doesn't matter if it's a ring or a straight chain, stuff like that. So what you're going to do is you're going to take one of the alkenes, and it's going to attack the hydrogen, right, and push off the chlorine. So you're going to make, right, so with that, and so you're going to want to put the hydrogen away from it, because what you really want to do is put the carbocation that's formed right next to the double bond. Okay, and the reason why we do that is because we can get a resonance structure, okay, to help stabilize it. So now's the carbocation's here, right, and the double bond is there. Okay, and remember we had a Cl minus. So if the chlorine encounters this version, it's going to attack there to make this product. If it sees this resonance structure, it's going to attack there to make this product. Okay. Now, now the other way that you could do this is to attack instead with the other double bond, right? And that's going to kick it this way. It's going to kick those electrons onto the chlorine. So you would make this product. So you put the hydrogen here, right, and the positive charge would go there, so it's right next to the carbocation. Okay, so again, you can get this resonance structure where you can move this guy over here to help out, and so you end up with the carbocation here and the alkene there, right? So with that, okay, so if the chlorine sees this this resonance structure, it'll make this chlorine. If it sees this one, it can attack there to make that. So that's how you do every single one. So you take one of the double bonds, attack, keep away, do the resonance structure, and have the chlorine attack each resonance structure. And then you go back and then say, okay, let's start over again, but now let's do it from the other double bond and do the same thing. Right? So you're going to add it here. You want the carbocation next to the other double bond, right? So with that, do the resonance structures and have the chlorine attack either resonance structure. So here are your four structures. Okay. Now for these aromatic, anti-aromatic, non-aromatic. Okay, so one of the things you need to do is you need to make sure that it goes all the way around the ring, that there's an available p orbital in there. Okay, so if there's a carbon, stuff like that. So if it has a charge, it has an available p orbital. If it's part of a double bond, has a p orbital. Okay, so if it satisfies that, you can go all the way around the ring, stuff like that. Then you look at what are called the Huckel numbers, and the way that I can never remember the numbers, but I can remember how you figure them out. So aromatic versus anti-aromatic. Stuff like that. So if it doesn't go all the way around the ring, it's this non-aromatic. Okay, but if it does, then it's either aromatic or anti-aromatic. Well, on the classic, the classic aromatic structure is just benzene, right? We know that this, and so what you're going to end up doing is you're looking at the pi electrons here. So there's 2 here, 2 here, 2 here. So the total is 6 pi electrons. Okay, we know that is aromatic. Okay, and so we know 6 is correct, and so you're going to go back and forth. So 6, 8, 10, 12, 14, 16, 18, 20, on down, and it goes the other way too, right? So that's 4, 2, like this, right? So it's going to go. So the numbers go, right, just like this, back and forth, and on down, right? Okay, so if it has this many pi electrons, it's aromatic. If it has this many, it's anti-aromatic. Okay, so for here, right, we are 2, 4, 6, 8, 10, 12. Okay, so that is, oh, that's on the anti-aromatic side, so it's anti. Okay. Now for this one, okay, now you have to be careful with the heteroatoms like nitrogen, oxygen, sulfur. Basically, what's going to happen is they're going to try to move the pi electrons such that it makes it aromatic. Okay, particularly if this thing is bonded to just has single bonds on it, you can actually sort of wiggle in order to get those electrons into the planes. So these orbitals are moving around like this. Okay, and so it can either move these lone pairs in or out of the plane so that they be counted or not. Okay, so for that, and so for this one here, right? So this is, if it's on a carbon, you have to count it. So 2, 4, 6. Okay, but so right now we're at aromatic. So what this the nitrogen is going to do is it's going to move these out of the plane so we don't have to count them. So for that, so this is going to be aromatic. Now, another example is something like this. Okay, so lone pair right there, right? So you have to count these 2, 4. Okay, so here, especially since this is on single bonds, it can move those orbitals so they're in alignment. Okay, and so you can count. So it does want to count those. So I'm sorry. So it ends up being its 6th one. And so with that, again, it's going to make it aromatic. So most of the time, so I'd say 95% of the time, if you have a heterocycle in there, it's going to be, and you can go all the way around, then it's going to be aromatic. So if you really do not know, odds are it's going to be aromatic. There's some notable exceptions, but for the most part, that's what they want to try to do. Okay. Now for here, right? So here and here, the problem with this molecule is that notice how right here and right here, these carbons don't have any p orbitals, right? They just have 4 normal sigma bonds, right? So like that, and so here the electrons can't go all the way around, right? So here they can go all the way around, but here if they're going to try, they'd hit here and not be able to go. So this is in fact non-aromatic. Okay, so there you go. Okay, so for here, right? So for that, so determine the major product. Okay, so again, this is going to be a good thing to go ahead and just do the mechanism so you can kind of work it out, right? So with that, so right, so that's gonna so the alkene is going to attack the H, push this away. So we have 2 choices. Okay, so we can either add the H here and put the carbocation there, or we can add the H here and put the carbocation there. And so now what you're looking at is the stability of the carbocation. Here it's primary, okay, because it only has 1 carbon attached. Here it's secondary because it has 2 carbons attached, here and here, right? So like that. So this is going to be a lot more stable. Okay, so you're going to have a lot more of this in solution. So when the chlorine attacks, it's going to attack here and here. There's just going to be a lot more of this around. Okay, so the 2 products would be here and here. Okay, but this is going to be the major product. Okay, so the Markovnikov. Okay, now for here we're going to do an E2. Okay, so here's the leaving group. So we need to look here and here on either side to see about making double bonds. As long as there's a hydrogen here, we can make the alkenes. So it's going to go here, right? So we're going to do on this side, okay, and then we're going to go on this side. Okay, so here's the original. That's originally where the leaving group was, right? So we went on either side. It's elimination, so we're going to end up with a double bond. So what you want to do is you want to see the fewest number of hydrogens on that, directly on that double bond. So the 4 bonds hanging off of here, how many are hydrogens, right? So in this carbon and that carbon, right? So this we have 3 bonds shown, so there's a hydrogen here. This carbon we have 2 bonds shown, so there's 2 hydrogens here. So we have a total of 3 hydrogens on this one. Here we have a hydrogen here, right? Because there's on this carbon, right? This is a carbon-carbon bond, carbon-hydrogen, right? Here again we have 3 bonds shown, so there's a hydrogen here. So this one only has two hydrogens on here, so this is going to be the major product because it has fewer hydrogens on the double bond. Okay, it's more substituted. Okay. Now for here, right? So these are the reactions to know, stuff like that. So for like this one here, this is the E2 reaction, right? So you make we just went over. Here you're adding HX. So X is a halide. Okay, so bromine, particularly bromine and chlorine, things like that. So you can add across. So for here, the mercury, this can also be mercury sulfate. Okay, so this is going to add HOH across a double bond, but the OH is going to go on the higher numbered side. So right, so this is tertiary, right, because it has 1, 2, 3 bonds attached. Okay, so it's going to put the OH on this one, as opposed to the borane peroxide, right? So for this one here, right, it's only secondary because it only has 2 carbons attached. So by that, so borane puts it on the higher numbered, or it's on the lower numbered side. Okay. MCPBA, right? So with that, so what you're going to do is you're going to take where that alkene is, right? You're going to put the epoxide right there. Okay. And with the stereochemistry, these guys, those groups and these groups are going to go together. So if these are wedges, these are going to be dashes. And, and if you want to make these dashes, then these are going to be wedges. But they have to be consistent. Okay. Here's another way. So these are different ways of making the triangle, or cyclopropane, right? So you put the triangle again right on that double bond, right? It goes away. So with that, but for here you end up putting chlorines on this at the peak of the cyclopropane. Here you just as a regular cyclopropane. Okay. For here you can have you can replace this. This works pretty well for tertiary alcohols. Some of that, somewhat with secondary. If you're going to do primary and secondary, these are probably thionyl chloride, SOCl2, PBr3, and PCl3. That they're probably going to work a little bit better for with that. So, but because these use an SN2 type mechanism, you actually get an inversion of stereochemistry. Stuff like that. So if you're so let's say this OH was on a wedge, then the resulting chlorine is going to be on a dash. So that's all of these 3 are going to use an SN2 mechanism. This is an SN1 mechanism, and so you're actually going to get both wedge and dash with your halide. So for the alkynes, for a lot of these things, they are just doing the alkane reaction twice. So by this, so it's like, so for here you're just doing the elimination twice. Again, we're going to add twice in here. This is, but the oxymercuration and hydroboration, that's where it gets a little bit interesting. So like that. So because what happens is, let's say you do this reaction here. Okay, you're going to take the double bond, right? So that you're going to take one of those pi bonds and put the OH there. Okay, it's borane, so it's going to be on the lower numbered side. Okay, but the problem is that is unstable. Okay. It's an unstable intermediate, and it tautomerizes to this. So you end up, right, so there's a hydrogen here. So you swap the position of the carbon-carbon, the double bond and the single bond. Okay, the oxygen still stays put. Okay, so with that, so here you're going to make the aldehyde for all of these. Okay, because they go through this similar intermediate. So for this one, the intermediate would look like this, right? And it's going to so here to there. Okay, so it's going to move around. So or the double bond's going to move around. The oxygen stays put. So, okay, so for here, the nucleophilic, right? So for that, so you're going to have a nucleophile come in and attack one of these sides. Okay, so this is partial positive, partial negative, partial positive. Okay, and so what's going to happen is, let's say here, and then that's going to break here, but the oxygen is still tethered. Okay, here are those 2 original carbons. Okay, and now it ends up making this intermediate nucleophile, but at some point during the wash, it turns into an OH, stuff like that. So now, under basic conditions, now we didn't talk too much about it, but just to let you guys know, under basic conditions, the nucleophile is going to want to go on the less substituted side because it's an SN2 type attack, and so it's going to want to go to the easier side to get to. Under acidic conditions, what ends up happening is you protonate the epoxide, and then that can open up to make a carbocation. So you want to make it more stable. So the more substituted, the higher number carbocation is going to be preferred, right? So that's where your nucleophile comes in, stuff like that. And so you actually get you swap the positions of the products under basic or acidic conditions. I'm not going to be on this particular test. I'm not going to be worrying about that too much, but but just be aware in the future if that's what's happening. Here, this is Williamson ether synthesis. It's just you're going to have an O nucleophile, right? You have a good leaving group, so that it's just attack here, kick away. It's just a classic SN2 reaction, right? Plus bromine, right? So there you go. Okay, so you're going to have predict the reagents, right? So like that, and so for this one, right? So you have an alkene, right? You're adding bromines across it on either side, so like that. So we don't have to worry about that one. So like that. So now these are both bromine, right? So if you did HBr, right, it would only add bromine on one side. You add hydrogen on there, so it can't be this. Okay, now bromine, you have bromine and water. Now with bromine and water, you get the halohydrin where a bromine's on one side and an OH is on the other. Stuff like that. So it can't be this one, so it has to be D. Okay. Now for this one, right? So with that, so we're going from an alkene to an OH. Okay, but notice how, right? So this one, let me fill in the dots here, right? So this is tertiary. This is the tertiary side of the alkene. This is the secondary side of the alkene. So we're putting that OH on the lower numbered side. So it's going to require this one here. If we were putting the OH there, we'd require the mercury. But since we're going to the lower numbered side, we're going to need to have borate, the hydroboration. Okay. So here, to predict the product, right? So with that, so you have your product here. Right? So you've got the Simmons-Smith, so CH2I2, zinc copper amalgam. So what you're going to do is you're going to make a cyclopropane right where that alkene is, and so you end up just making this. This is just a side chain, so end up making that. PBr3 again. We're going to swap an OH for a Br. Okay, so with that, so we're going to put the Br here. So Br. So pretty right. So with that, so we have an alkene, right? So with that, so that's gonna we have Br, right? So with that, so right, so that's gonna go here, right? To make put the Br here, right? Carbocation, right? And then the Br minus is gonna come in and attack. So we end up having, you just put bromines on either side. Like that. So just on either side, so we're going to put a bromine here, right? Bromine there. Okay. Now we have the mercury sulfate, right? So we're doing oxymercuration. So this puts it on the higher numbered side, so of the double bond, right? So for this one here, right? Right. So this has 1, 2, 3. Carbons attached, so this side's the tertiary side. This one here, it only has 1 carbon attached, so it's going to there. This goes on the higher numbered side, so we're going to put the OH on this side. So it ends up going there. Okay, so again we have the epoxide, right? So with that we have our nucleophile here. So remember that these are going to be, it's going to be attracted to this to the partial positive here, right? So that goes there, and we're going to break this bond. These 2 electrons are going to go up onto the oxygen, and so the oxygen is still tethered, and so you end up with that. But after the wash, you end up with an OH. Stuff like that. So okay, so you're going to get an OH on one side and your nucleophile on the other. In this case, it's chloride. Okay, again here, right? So with that, so we're going to attack there, right? It's just an SN2 attack there. No, like that plus Br. Okay, Now I did screw up because I rewrote this. So that's the one we just did. But again, for here, right? So with that, so you have, right? So with that, so you have borane, right? H2O2. So you're gonna do hydroboration. So you're gonna go through this intermediate here. Oop. Right, so if that's right, so this is a secondary, right? Because it has 2 carbons attached. This is the primary, so we're going to put the OH on that side. So it's going to make that intermediate, but after it makes this, right, it's going to tautomerize to your product. Okay, so there's a hydrogen here, so let's go there. Okay, so those are the types of questions you'll see. So with that, so good luck.